Hello everyone, welcome back to our next video on group theory. In this video, we are going to go over group theory isomorphisms. I'm so excited to start, so let's begin. So let us recall what a group is. And to define what a group is in group theory, we use the axioms of group theory. So for all A and B are elements of G, for all elements A and B and G, A operated with B should also be in G. Second, A operated with B operated with C should equal A operated with B operated with C. So the order of which you evaluate the operations shouldn't actually matter, like under a change of parentheses, right? Where A, B, and C are elements of some group G. Third one, there must exist some identity elements. This is important. That's a member of the group G, such that A operated with E is going to be equal to A for all A is some element of G. Lastly, there must exist some inverse element I that's a member of G, such that A operated with the inverse I is going to equal the identity element for all A is in G. Alrighty. Now there is one thing though. The identity element though operated with E is actually going to output I. That's the one exception to this rule. And with those four axioms, we have what a group is. So that's the definition of a group. If any of this is unfamiliar to you guys, I recommend watching my last video on group theory. Watch that one and you'll understand what a group is. And yeah, so watch that video. In this video, we're going to talk about group isomorphisms. So what is an isomorphism? Well, to talk about isomorphisms, we first need Cayley Tables. So, Cayley Tables are just some way to kind of organize group operations. For example, say I have some group G. Okay, let's just call it G, the classic G. And it consists of elements E, A, and I with some group operation, big plus. All right. Now, of course, E operated with A is going to be A. E operated with I is going to be I. A operated with I is going to be E. Now, let's define A operated with I. That's going to be equal to, what should A operated with I be? A operated with I, let's let that be E. Oh yeah, it has to be E by definition. Yeah, I forgot, sorry. What other combinations do we have here? We have E operated with A, we did that one, A operated with E. Oh, A operated with A, that's the important one. A operated with A, let's let A operated with A be equal to I. Okay? And actually, A operated with A has to be I for this to be a group. I'll let you guys prove that yourselves. Basically just use these axioms and you can deduce that A operated with A ought to be I for G to be a group. So we can actually organize all of these group operations. It's one clean table. Now, if you guys remember from 3rd grade, blast from the past, we learned about multiplication tables. Kind of a bit hard to spell. Right, we have some operation, multiplication, the X sign, X marks the spot. We have like 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, all the way to like how much numbers you need to memorize, right? And you have, okay, 0 times 0 is 0, like all this is 0, trivially, right? And you have 0 times, and you have like 1 times 1 is 1. 1 times 2 is 2. You have like 3 times 2 is 6, for example. But you need to take any two numbers and you can have make like a 90-degree angle between them, and it like marks the answer to that number, which is like 2 in this case. So we kind of generalize the concept of the multiplication table in group theory, and we call those Cayley tables. And they're really awesome for organizing things. Organization is key in group theory. So, for example, let's make a Cayley table. So in this case, we have an operation, a big plus. The big plus is not any specific operation. It's just some general operation of the group, and we define how it operates with elements here. And what we want to do here is organize all of this. So we start by just writing out elements of the group, EAI, just as we write elements of the integers, the positive ones here, or the non-negative ones here. So E operated with E, that's going to be E. E operated with A, that's going to be A. Here's going to be I, trivially. A operated with E, that's going to be A. A operated with A, remember that's going to be I. It has to be I, actually. And we have A operated with I, it's going to be E. I operated with E, that's going to be I. Yes. I operated with A. I operated with A is going to be E. And I operated with I is going to be E. And this is what we call a Cayley table. And basically, we just take two elements here. We kind of like cross them together to get what the operation is. There's some way of organizing this. Now, say I have, let's make another group, H. Let's do this on our new page. So let's recall we had G was E, A, I, so an operation, and we had this Cayley table over here. E, A, I, E, A, I. Just rewriting down what we had last time on a new page for organization. This was E, and this was E. Okay, so you have some new group. Let's call it H. You guys probably predicted that one because H comes after G. And let there be a function F that acts on the elements of G and outputs the elements of H. We have a function now. Interesting. So H, the elements of H it's going to be F of E, F of A, F of I, and say that H has a different group operation. Let's call it the general wedge operation. Okay, so what is the Cayley table for elements of H? Well, I have wedge here. I have F of E. I don't have to put any comma here. F of E, F of A, and F of I. Same thing down here, F of E, F of A, F of I. So now we're going to have here, this is going to be F of E, wedge, F of E. Okay, F of E, wedge, F of E. You're going to have F of E, F of A, wedge, F of E. And so on. Gonna run out of space a tad bit. F of E, wedge F of A, F of A, wedge F of A, F of I, wedge F of I, near F of E, wedge F of I, F of A, wedge F of I, F of I, wedge F of I. So all we're doing here is we have a function here, and we're just writing the Cayley table, the general Cayley table for this function over here. Now, let's actually kind of rewrite this group in a way. Let's rewrite this in the more general form. So you have EAI, big plus EAI. Remember, this is this E operated with E. This is E operated with A. E operated with I. A operated with E. A operated with A. A operated with I operated with E. I operated with A. operator with I. So all we're doing here is just writing these in the general sense. Of course, these are the values, but let's write this in the general sense. Just as we wrote this function in the Cayley table for the elements of this function in the general sense. So remember, there's a function that acts on the elements of G. So this is like G, right? And it maps it to elements of H. And let's actually define this function in a way. So E, of course, is going to map to f of E. A will map to f of A. You guys get the point, right? So I just have E, A, I, some operation. I have f of E, f of A, f of I. And these are just mapping. We just have a mapping. That's all a function is, a mapping. Okay? And something that's pretty cool here, right? Not only are the elements of G mapped onto elements of H, like we could have cheated here, like we defined the elements of H as functions of G, but not only is there a mapping between elements of G and H, but it looks like the actual operations of elements of G are sort of mapped on to that of H, right? Because here we have E operative E, have f of E, wedge f of E. A operative E, f of A, wedge f of E, right? They're kind of mapped to each other. So, like, for example, f of A operative E, that's going to give me f of A, wedge f of E. Because, like, these will, not only are the members of the group being mapped to each other, but the group operations, they're being mapped as well. So this is like where the whole pie comes together. That's what I usually say. Like, everything comes together here. We could literally relabel E, A, and I to f of E, f of A, and f of I, and then relabel E operative E as like f of E, but wedge f of E. So really, we're just relabeling this operation to the wedge. And then these are the same. All we really did here is we just relabeled the elements of the group. You can check this out yourself. We relabeled these elements with the functions of them, and we relabeled the operation symbol with the wedge symbol. All we're doing here is just rewriting the same exact group. It's like the fundamental structure of these groups are the same, they're just relabeled. And this is a very profound fundamental notice here. You guys may not appreciate it now, but in the next future videos, we're gonna show how this is such a beautiful idea. Because these groups, there's a function between these two groups that we've defined, and this function is assigning elements of one group to the other, and the way it assigns it is just a relabeling. All we're doing here is just like repolishing the elements of the group. And to say that these groups technically aren't the exact same group, right? There is still a G and H, but fundamentally it's really just a rewriting of the elements. And if there's some property of this G group, the same property must also hold for this H group, since all we have here is a relabeling of elements here. So, like, if, for example, G is abelian, if you don't know what abelian is, check out my last video on group theory. If G is abelian, well, then H will also have to be abelian. If G is cyclic, for example, H will also be cyclic. So if E is the element of G, E will also be the element of H. Like, these properties carry on. So if we want to prove something in group theory, we want to prove that the integers are like cyclic, for example. Or actually, no. We want to prove that some group, let's call this group M, is cyclic. And we already notice that the integers are cyclic, and that Z and M, and the integers and M are isomorphic to each other. That's what we call it. then we don't have to really prove that M is cyclic. If M and the integers are isomorphic, well then if Z is cyclic, or Z being the integers, then M is also cyclic. So we can kind of like prove one thing, and that proof will apply to everything that is isomorphic to that group. Now I haven't actually defined what isomorphic means, and we say that two groups are isomorphic to each other if the elements are really just relabeled once the function acts on them. There's really just a relabeling occurring. Now, of course, we haven't really rigidly defined what an isomorphism is. Or let's add some light here. We haven't rigorously defined what an isomorphism is. I'm gonna get to that, but I just really want to kind of nail this concept in your head that it's really just a relabeling here. So it's not like we have to define what an isomorphism is. So we say that an isomorphism. Let's make two definitions. So our first definition of an isomorphism, like the idea we have to capture here, is just relabeling, like the elements of some group and being functioned onto another group as just being a relabeled thing. So we might want to say, okay, well, an isomorphism is just an injective function, right? It's injective. That's what it is, right? Since there must be some unique pairing of elements of one group G to the elements of H, right? But not quite, right? Like we can't have an injective function that's not surjective. Surely we want the function to be defined for all elements of G, right? Because if we don't do that, then it isn't really much of a relabeling. Since we have extra elements that don't have any label, right? So it can't be injective. That shouldn't be our. The injective functions won't capture the idea of a relabeling. We might say, okay, what about bijective functions? Bijective functions are injective and surjective. Surely that will capture this idea. And so that is also a no, because we can have a bijective function where it's a unique pairing between elements and is defined for all elements of G. However, we've only captured half of what we want to capture. Because remember, there should also be a relating between the operations, between the elements of G onto H. There should be a function that sends E operated with E to F of E, wedge F of E. Sorry. There should be a function that sends E operated with I to F of E, wedge F of I, and bijective functions don't care about how operations work. They only care about just assigning the symbols of some group to the other group. But we don't really. But caring about symbols is only half of the picture. We also want to capture operations. So the third definition that we can use is that an isomorphism is a function that acts on A operated with B and gives us F of A wedge F of B. And I say, well, this is a weird definition for an isomorphism. Again, we're trying to capture the idea of a relabeling here, and that we call that idea an isomorphism. So how is this a good definition for what we want to do? Well, look, here I have E operated with E. We send it to F of E, wedge F of E, for example. Really, what we're saying here is that F of E operated with E is F of E wedge F of E, right? Take F of E, put a function on that, F of E wedge F of E. Take F of A operated with E. Send it to F of A wedge F of E, right? F of A operated with E. That's F of A wedge F of E. So we can generalize this to say that F of here, we probably shouldn't use A, right? Since that's already in this thing. We can generalize this to say F of W operated with B equals F of W wedge F of B, where W and B are just some elements of some group. Let's call this group big A. and the f of w and f of b are elements of some group. Let's call that big B. And f is an isomorphism between elements of A and elements of B. This captures the idea that we want to. If you have a function a function of two elements being operate together, and it gives us that function, but operated with the other function of their respective parts, then that's an isomorphism. Where this plus symbol is the operation for A, and this is the operation for the group B. And if a function does this, we call this function an isomorphism. So I hope that made sense. Let's just do a brief recap. The basic idea I want to show is relabeling between groups. That was our most basic idea. For example, here, let's give a similar example. Say I have EAI again. Let's have a Cayley table. We have E operative with E operative with A operative with I operative with E operative with A operative with I operative with E, I operative with A, and I operative with I. And then I have another group, Wedge. You don't have to use wedge in this symbol specifically, just some general symbol. And I have this group. Let's just call this group, let's say, hearts, square, and triangle. Okay, because that can be a group. Here we have heart, wedge, heart, wedge, square, heart, wedge, triangle, square. I forgot what the symbol was. Square, wedge. This is a triangle, by the way. Excuse my poor drawing. Okay. Triangle, wedge, square, triangle, wedge, triangle. Okay? So these are our two groups. Let's call this G and H. Now these two groups have the same exact structure, because E can just be relabeled to heart, A can be relabeled to square, I can be relabeled to triangle, okay? And then this symbol can be relabeled to wedge. And then we have the exact same thing once we've just relabeled everything here. And these two groups are isomorphisms since there exists some function that acts on, what was it again? W and B, that equals f of W, some function that acts on W operative with B, gives us f of W, wedge f of B, where W and B are just some general element of G, right? Then f of W, f of B are just some general elements of H. Since we have a function, like I can take this a function, acts on this one, function of E operative with E, and we'll assign it, guess what? F of E, which is heart, wedge f of E. And these two groups are isomorphic. So that's the big idea of isomorphisms. That's what they are. To define it rigorously, it's a function that acts on some element or operates with another element and returns this over here. I'm not going to say it again in English words. And this simple idea just captures everything we want about relabeling of groups. And if you prove one thing about this G group, it will apply to this group as well, since all we've really done is just change up the symbols a bit, right? Change up symbols didn't change the fundamental structure of the group, and that's what we call an isomorphic group. An isomorphic group are groups where there exists an isomorphism between those two groups, and isomorphism is a function that satisfies this property. Hope you guys enjoyed that video. And yeah, if you enjoyed this video, please consider sharing it, and have an amazing day. See you guys next time. Bye.